Good evening, everyone. Welcome to 7th live session for the course Functional and Conceptual Design from IIT Madras. My name is Neelarnab Dutta, and I am a PMRF fellow and a PhD scholar from Department of Design, IIT Guwahati. So the agenda for this class is to help you with week 7 assignments. So have you gone through the lecture videos from week 7?
Yes, some.
Okay. So the deadline for assignment is tomorrow, 14th September. So if you have not finished the assignments, please finish them on time. And this particular session will be conceptual because the nature of the assignments are objectives. So I will try to cover some of the key concepts that will help you in solving those assignments. Okay.
Yes, sure.
Okay, so what we learned in the last class. So, have you attended the last class?
Yes.
Okay, so I'll briefly talk about some of the key topics from last class. So, one is constraint versus function. So, after we come up with our specifications, like the product specifications, we know the nature of the specifications are a matrix plus a value, right? For example, 50 kg. So this kg is a matrix, that is the weight, and 50 is a value. So some of these specifications you consider them as constraints in your design, and some of them are functions. So okay, so which of the functions you use as a constraint? For example, you want to design a bike, and weight of the bike has to be less than 180 kg. Okay, and another specification can be like luggage carrying capacity is to be like 155 kg. Okay. Okay, so tell me, which among these two, which is a constraint and which is a function? Both are specification, product specification, but during design you consider one of them as function and one of them as constraint.
Weight of the bike less than 180 kg is a constraint under which we have to design the bike, and luggage carrying capacity equals 155 kg. This is a function that we have to maintain. At least it should be able to sustain this much luggage carrying capacity.
Okay, and why you define this one as a constraint and this one as a function?
As above one is restricting the weight of the bike with a metric value. That's why I consider this weight of a bike is less than 180 kg is a constraint for the designing of the bike.
Okay, so basically we define constraint and function from one perspective, that is, can we solve or can we work on that particular specification? Okay, so when we design a bike, we can actually design for luggage carrying capacity. So we can actually design the chassis, we can decide upon the thickness of the pipes, we can also play with the structural arrangement, and we can actually design for carrying 155 kg. Okay, but weight of the bike less than 180 kg is not something we can decide prior to deciding all the various components, because a bike may have a fuel tank, then we have chassis, we have engine, then we have the chassis, then the seats, wheels. Okay, so at the end at the end only we can think about like what is going to be the weight of the bike. So we don't actually have a direct control on the weight, but it's a uh, it's a number that we get after deciding various components and various parts of the particular design. So we kept that as a constraint because we cannot go straightly deciding on the that particular specification. We cannot design upon that, but we can design upon luggage carrying capacity, so we consider it as a function. Okay, so next what we learned in last class was functional decomposition. So what is functional decomposition? Do you remember?
Yes, in functional decomposition, we give actually use fast method to identify all the functions of individual parts uh, of a product.
Okay, so functional decomposition is basically breaking product functions. You have a higher product function, right? So product functions into individual sub functions. So basically we are decomposing sub functions. Sub functions. Again, sub functions can be another sub functions. So this particular process of breaking down the higher level functions into smaller functions, sub functions, is known as functional decompositions. For example, I discussed last time, like design like functional decomposition of a mixie grinder. So the overall objective is to grind masala. So grind masala, but when you move to sub functions, it will come like rotating blades, then storing masala, like that, then easy to clean. So these rotating blades can be electrical motor. So like that we break down the higher level functions into smaller level functions. So we discussed two methods. One was SOP method and one is fast method. So what was SOP method? Do you remember?
Yes, in a SOP method, we actually uh, one by one remove all the components and try to identify its function in a product.
Yes, correct. So we start removing the very smallest, possible functional block, and then after removing, we then start operating the procedure, and we try to analyze the relationship and what function miss when we operate without that particular functional block. And after we do this particular task iteratively, we then come to know what are dependencies, who is a child and who is a parent. So these parent child relationships can be easily analyzed by using this method. So slowly after many iterations, we actually come to know about the various functionalities and sub functions. However, there's a limitation of this particular method. One is that this is mostly useful for reverse engineering because you need something already existing. Okay, so for new product development, this will not be helpful. Again, there are issues like sometimes there are some functional blocks. When you remove, you may not see visible change in the functionalities. For example, if this is something like a glowing LED, okay, and you have three components, and probably just removing one particular component may not result in change in the parent level function. So we may not know what is the use of this particular function. So we'll feel that this is something redundant, but actually this way of analyzing functional functions more like a black box is not always helpful when we do not when this kind of relationship or characteristics does not reflect when we remove something. The other method was fast method, and the benefit of this is that this can be used for new product development also. So what we do here, we make two lines. We start actually from the output to the input. So here is the output, which means the highest high level function, and then as an input we consider something assumed function like input like electricity, right? Very basic one. And then we start asking how, like we if for example, for a mixie grinder, if high level objective is to grind the masala, then we ask first how. Then you say, okay, you grind it. So how to grind? You say using blade. Then how? You say rotating blade. Then how to rotate? Using motor. How to rotate motor? Using electricity. So like that we connect from output to input, asking the question how, and we verify the same thing, asking the question why, from left to right, from input to output. Clear?
Yes, sir.
Okay, so what was the name of this particular functional part? Do you remember?
Critical path concept.
Yes, this is critical
Critical
function
path.
function path, and you have then under every critical functional blocks we have sub functions. Okay, so these are sub functions, and in this fast method we can also detect various unwanted functions, for example, which are not desired, but because of the system design you may realize that certain noises starts coming. So those are not desired functions, but those are resultant of some other function. So those are called as unwanted functions. Okay, and there are again one-time functions. For example, when you want to transport particular product, so packaging and transportation, safety, protection, all these things come as one-time function. Okay. So after we develop that, we use something called function tree to represent the particular function and sub functions. Okay, so this particular functional tree is helpful when you actually try to convert and go for product form design or product architecture design, because this is the basis. This is the on the basis of this particular function tree you can next move forward for working on functional architecture, that is the product form. So this was what we learned in the last class. So one thing I like discussed in the last class, that these two methods are actually used, are these are simple methods, okay, simple techniques, and these are used for only simple products, okay, because as the complexity of products increases, there are dependencies arises between different functional blocks. So it is not very easy to represent a complex product using just a simple functional tree. Okay, so I'll start today's session with a new concept, which is functional common basis. So what is functional common basis? So what we do in functional decomposition is we break down a high level function, high level function into sub functions. Okay, and then we again break down this first level function to second level sub functions, and so on. Okay, but what is the point where we stop functional decompositions? Okay, because this particular process can be extended, you can keep on decomposing particular functions into sub functions till you reach something at the level of like pure science level in terms of physics, chemistry. Okay, so in order to understand like where we can stop functional decomposition, we need to understand something called common basis. Okay, so you might have remembered like how to define a particular function. So a function is written in a functional decomposition process in the form of a verb plus a noun. For example, for this particular trimmer, we can write trim beard. Okay, so trim is a verb, beard is a noun. So this is how we write function in a functional decomposition process. So we then move to the next level, then we write like a rotate blade. Then we move forward, how we rotate the blade, we use using motor. Okay, it's not the way it's right, you have to write, you need to write like convert electrical energy into rotational energy. Okay, after that it is electrical energy. So electrical energy is the input and trim beard is the high level output. So just see here, when we try to break down a higher level function to a lower level function, we end up with something like a verb like this: convert, rotate, something like that. So these are actually the basic functions where we want to reach via this functional decomposition process. And at the point when we reach something like convert electrical energy to rotational, you should understand that we reach the end of functional decomposition process, because these are some of the very low level functions. After that there is no requirement for further functional decomposition. So for example, this can be convert electrical energy to rotational energy. Okay. So this can be like change direction, or regulate rotational motion. Okay, something like that. So after that you can directly come up with the input. Okay, so rotational motion, so what will regulate rotational motion? Probably some human input. So likewise, so there are certain classes defined along with respective functions which are used for defining the functions in a functional decomposition process. And when we reach this sort of verb in a verb form, we should understand that we have reached a lowest level functional decomposition process. The advantage of using functional common basis is that this particular vocabulary for defining functions are common and to various disciplines. And again, it's a robust way how one can understand particular function. So someone might have different vocabulary. For example, for rotating a motor, someone can write rotate, rotate blade. For example, rotating a blade, rotate blade. Someone can write spin blade. Okay, so likewise people may use different verbs for the same meaning, but using different version of the function will bring confusion when you work in a team or in an organization. So use something very basic which comes under functional common basis, so that everyone, when you move from design stage to the concept phase to the development phase, people still know what individual function means. Okay, that's the reason why we should have something common. Again, common representation to compare product across domains. So for example, even it is electrical, electrical device or a mechanical device or a medical device, at the start probably you might have different verbs. For example, the example I gave in the last class was grind spice grinder, right? The grinding machine. So the very first high level function was grind, masala, right? And the high level function of this particular device is trim beer. See the difference between the function. One is grind, one is trim. Okay, but when you break down the higher level functions to sub functions, then to sub functions, at the end when you reach the basis function, the basic functions, then it's same across all various disciplines, whether it is electrical product, you at the end say only these things like actuate, rotate, or convert, like that. Okay, and this defined a level. So basically functional common basis, this particular functions define a level when a designer should understand that we have reached the end of the functional decomposition process and we should stop the process further. Okay, clear? Okay, so 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 next we'll discuss about how to do functional decomposition for complex product. Okay, so in the previous class I have discussed about SOP, then fast method. All of them are useful for simple products. Simple products means why they are simple? Because they have one simple critical function path. So they have one single, so which have a high level output function and a starting input. Okay, but when products became complex, like something like a bike which have lot of different high level functions. So what are various high level functions of a bike? Can we answer? Okay, sorry for the interruption. So basically in high level products, you're right, like the very first function is what? To run the vehicle. Okay, so running the vehicle is probably the very important high level function. The second important function can be carry luggage. Okay, people should for when someone wants a bike like Royal Enfield or like a classic bike, people might have thought about carrying luggage for a long ride. So this that can be a high level function. Another high level function can be like navigation. Okay, so accurate, give navigation. Okay, see the way I have written: give verb plus noun, run the vehicle, carry plus luggage. Okay, it's like verb plus noun. So what happened when we try to use these methods? First of all, since SOP method cannot be used, because even if we remove something from this particular high level function, for example, if you remove something from the navigation system, it will not impact the vehicle running condition. Even if we remove something that carry the luggage, it will again will not hamper the vehicle running condition. So as I told you before, in SOP basically we try to see the relationship. Whenever we remove something at the very bottom, at a very low level function, we try to run and operate particular device and see what sort of functionality lacks, and then we try to define the particular function. But in case of complex product, if we adopt such strategy, it will not help. The if we remove something from navigation, the bike will still run. That means you'll never know what this particular product is. Similarly, in case of for fast method, what happened, like fast method probably can give you three different critical function part. Okay, so one having inputs. Okay, so what are the inputs for running the vehicle? So for running the vehicle, probably it is the human effort in acceleration, right? So basically, you are moving, rotate the accelerator. So rotate accelerator. So this is the initial input. For luggage carrying, the input are luggage basically cloth, other commodities. For navigation, so input probably is GPS. So output is what? Give navigation. And if we see luggage, it is like carry luggage. And if we consider accelerator, it is run the vehicle. But using fast method, it is not possible to understand the relationship in between the critical paths, which generally happen in case of complex products. So basically, complex products have multiple critical function paths. It cannot be represented by a simple function tree. So in case of simple products, there can be like simple hierarchical, like a functional tree. However, in case of complex product, you have lot of parallel trees happening, and there are relationships in between. So at the end, this is not a tree structure, it end up something like a structure, which is called function structure. Okay, so complex products functional modeling is done, and you end up developing something called function structure instead of function tree. Okay, and the third point is like a complex product have critical function parts which have dependencies, interdependencies among themselves. Let's take an example here. So basically, the method we use for complex for functional decomposition of complex product is called flow model. So in flow model, what we do, we consider the overall functionalities, okay, as black box. Okay, we consider the product as a black box. We don't know anything about, we don't know the functionalities initially. What we only consider are the inputs, the input flow, and the output flow. Okay, so sorry, the direction of this arrow should be the other way. Okay, so generally, any product, any complex product, the inputs and the outputs can be divided, can be classified into three categories. One is energy. For example, in case of a bike, the energy is what energy? It is the rotational motion. How? So you rotate the accelerator, right? So rotation. Okay. So it's a mechanical energy. Okay. Rotation, mechanical energy. Then there can be also energy like battery. So it's a electrical energy. Basically potential energy, electrical energy I'll consider like a battery. Then other sort of inputs, energy inputs can be fuel. I will not consider. Okay, fuel I will not consider as energy. Fuel I will consider as material. Okay, so basically, uh, in a flow model, all sort of inputs can be classified into three categories: energy, materials, and information. And these are again the outputs of the system. So whenever a particular energy enters as an input, there are some other form of energy that comes out. Okay, so for example, if an input is a rotational energy, or some electrical energy, or some heat energy. Now I'm saying heat energy because there's an IC engine, internal combustion engine. So at the end, the heat energy is converted into rotational energy. So what we are getting at the end is kinetic energy, right? That's why the bike moves. Similarly, material wise, there are materials apart from the raw materials. There are materials like fuel. Okay, there are other raw materials which also goes. Okay, like foam, cushion, tire, air in wheels. Okay, so like that, there are a lot of different materials that can be input to the system. In terms of information or signal, so these are like the controls that the user wants to give to the particular to the product. For example, for a bike, it is first signaling, like signaling like going left, right. Okay, so all those information. Then it can be the GPS, right? The GPS is an input signal. And then what? Probably the key. When you first enter the key, the bike starts. So that's a signal. In terms of energy, when you provide rotational motion, at the end the bike moves. It's converted into kinetic energy. See, you rotate the accelerator, the bikes got a kinetic energy. You use fuel, okay, at the end you get exhaust gases, right? You use information like key, you enter key, so what you get a sound as a signal that bike starts. Okay, so likewise, what we try to do after we get to know about these inputs and outputs, we try to analyze the various functions that actually comes intermediately, and then we try to define how we at the end reach this particular form of output. So it is very similar to fast, but a bit different, because in fast we only consider one particular type of input. Here we consider various type of input, and those various types of inputs are classified into three broad categories. So overall, when we try to do all, we try to define various functions, sub functions, second level function, third level function, we end up creating a functional structure having numerous interconnection in order to achieve the final outputs. Got it? Okay, so things will get clear once I give an example, so please bear with me. Okay, so let's give an example. Okay, so this particular method is also useful when we try to when we go for a new product development. What happens in case of existing product? We already know that a particular product is simple or complex, because we have a past experience, like we know based on our experience that a particular product is complex or a simple product, because we have seen similar products. But when you try to develop a new product, we may not know what are various high level function we may require, if we need, do we need multiple critical paths, or single critical path? That part we don't know initially. That's the reason why it is always better if you choose something like a method which have capability to this, to to correlate various functions. It should not have any sort of limitation while modeling the functional blocks. Okay, so that's the reason why when we try to do new product development, new product design, we use this flow model for functional modeling. Okay, so let's take an example. So in my first or second class, I have discussed something about a sachet dispenser. So this was the scenario. What happens, like in a mall scenario, we do not have sachets, we have only shampoo bottles. Okay, and whenever you ask a person in a mall, he will say, ma'am, we don't have these sachets, we have only shampoo bottles, because it is not easy to manage the shampoo sachets. Okay, and there are no places to store all these things. So that is the reply of a person in a mall scenario. So this comes from a contextual inquiry that we did previously. Similarly, when we ask someone, in a retail store, they have all sachets, but they store it in a very frugal manner, and it is very difficult to manage their sales, because very difficult to search a particular strips of shampoo. You have different brands, and it also very difficult to cut particular number of sachets, long sachet strip. And whenever there's a sachets comes uh, to an end, you have very few sachets left, it is not also possible to hang them in a string. So keeping that in mind, what we proposed was a automatic sachet dispenser. Okay, so if that's the initial scope that you know we formulate, okay, at the initial phase of product design, then we have to come up with functional modeling after we set the specifications. For example, we have set certain specifications. So so these are some example specification, okay, for your understanding. So let's say the device should be able to store at least 50 number sachet. Okay, so 50 units, that means it's a 50 value, unit is a matrix sachet, so number of sachets that it can store. Then the second thing is like this sachet, it should dispense multiple sachets at one go. Okay, for example, if you ask 5 sachet, it should dispense sachets in a strip form, not like individual sachets. Okay, so you can have a number like, so dispense sachet like 5 units, okay, per strip. So it's an example, like 5 connected units minimum, so it's like greater than 5, so minimum 5 units should be there in a strip. Okay, similarly, it should cut. Okay, so cut uh, precisely, okay, within a very short period of time. So all those can be your specifications. But once you have the specifications, and when you then finally understand that what are the constraints and what are the functions, you have to at the end develop the functional model for such a device. And since you do not have a prior exposure for such a device, you need to rely on some of these modeling techniques. So we use here the flow model technique. Okay. Okay. So I have intentionally put this particular text over the model, the concept behind, because sometimes we may not even have the conceptual level understanding of the product itself. So in those cases, when you do not have an understanding of the conceptual level or the form of a particular product or the architecture of a product, we have to go in a systematic way, from functional modeling then to architecture design. Okay, then you move to the product design. So that's the reason why I just upload this particular graphics with this particular text. So let's see how functional model us will help us in defining the product architecture. Okay, so let's do the exercise. Okay, so here, as we understood that we have three different kind of inputs and three different kind of outputs. So one type of input is energy, second type of input is material, okay, and third type is signal. I represented these like thin arrows means these are energy. The double arrow, okay, means these are material, and the dashed arrow is a signal. Okay, so let's try to understand like what are the various inputs in this particular system. Okay, so what are the various inputs? Okay, so what you want to you know have inside this particular device, what sort of input output you want to see. Probably you may think like, okay, this system probably needs some sort of electrical energy, so you say like, okay, electrical energy. Okay, electrical energy is an input. Probably it's a device, that's why it needs some sort of power. Then you say, okay, probably human intervention is also required because we need to press certain buttons. So in terms of energy, we also consider human energy. Okay. Okay. In terms of material, we have sachets. Okay, because you need to first store sachets, then only you can get it dispensed. Okay. Okay, and then signals can be like device on off. Okay, then define the number of sachets. Okay, so define sachet requirement. Then like you give something for starting the dispense. Okay, something like that. So these are some of the signals that you can give. So what you want as output? So probably you may assume at the initial phase that since it's a mechanical system and it will dispense, it will drive some motor, so definitely there will be something like a sound. Some sort of sound probably will come. Okay, then probably you may think like, okay, maybe if there's a sound, probably some sort of heat also may generate. Okay, so these are your assumptions initial level. In terms of sachet, as a material output, you will get sachet. Okay, and what you will get in terms of signal? So basically confirmation. Okay, you get the confirmation that it's dispense. So dispense confirmation, using some sort of noise, some sort of, sorry, buzzer or alarm. The system notified you that the task is done. Okay, so that sort of output you can assume. Okay, so let's see how we can you know think about breaking the high level functions into these inputs into some functional blocks. Okay, so this electrical energy, maybe first converted into something like a, because this is 220 volt, probably you need to convert into DC. Okay, so so step down electrical energy. Okay, then probably convert to DC. See, I'm trying to use those, basic functions, so that you know that we reach at least at some level of functional decomposition. So this doesn't mean that we reach here, but we know that for a particular, task like converting electrical energy to DC, the this is the level where we can reach. After that, when we convert to DC, probably you can think about, we will, trigger something like a, dispenser, some sort of dispense. Before dispensing, we need something like a, like a power, some sort of processing unit, right? Because there should be some sort of processing unit which will give signal, like, which will detect how many sachets needs to be, dispensed. Okay, so there should be some sort of processing unit. So you are, transmitting or supply to processing unit. Okay, then probably, supply to the supply dispensing unit. Okay, then probably supply to the cutting unit. These can be different mechanism, that's why just I'm writing. So after that, what? So supply to the processor. Okay, so let's leave here and we'll start doing the others. So what we'll do with the sessions, when you take sessions as inputs, you probably, um, stack stack the sessions inside. Then you, okay, we'll use double line here, okay, so that we understand this is a material sachet. Then we use, we store sachet, sorry, sachet. And then we, uh, feed. Okay, but feed to what? We feed it to the dispensing unit. Okay, so supply dispensing unit, supply. Okay, there should be some sort of dispensing unit. Okay, let's see. feed feed to dispenser. Okay, okay, so, okay, let's start with the other, signal. So when we first start and it, detect, so we need to, provide some input. Okay, so detect input. Okay, so detect input means user input, so that means there should be some sort of, processing unit. So process input, right? So process input means it detects like how many sessions you want. Then what you probably, um, actuate. Okay, actuate, probably the dispenser. Okay, okay. Now see the relationship it is trying to establish. This particular input is actuating dispenser. So there is a dispenser. Think about, there is a dispenser. Okay, this particular thing is actuating. Oh, sorry, this needs to be signal. Okay, all, let me erase this, because these needs to be in the form of signals. Okay, okay. So if there's a dispenser, that means it will actuate the dispenser. It's giving a signal, okay, to the dispenser that start it. Now this particular sachets are actually fed to the dispenser. So that means from here we can have material fed. Okay, and the electrical energy is now supplying the power. See, now together the dispensing system is running. So what happened? The dispensing mechanism, when it dispense, it needs to detect, right? So it cannot dispense the all the shampoo sachets. It needs to stop at particular point. Okay, so it should detect the count. Okay, so then what? So after actuating, the next thing, it's like sense sachets, right? So basically you need to sense the sachets using some sort of sensor. Okay, so that means next thing is you fetch the sense data to what? To the dispenser, so that the dispenser stop. Okay, after detecting certain number of sachets, whatever inputs is been provided, the dispenser stops. Okay, okay, so these sensing, fetching, all the things are done by something like a processor. Okay, otherwise, how logically the system is able to understand, like, okay, like stop the dispenser or run the dispenser. Okay, so all these decisions, for making this decision, you need something like a microcontroller unit. Okay, so the electrical energy are supplied to this MCU. Okay, and this signal is first actually fetched to the MCU. MCU means microcontroller unit. And then the MCU give the signal. Okay, so these are all signal. This is sensor signal. This is like the electrical signal. So it is giving the control signal to stop the dispenser. Okay, so what happened next? Now, when the dispenser stops, now the sachets needs to be cut. Okay, and then delivered outside. So that means the system needs to have some sort of cutting, some cutting mechanism or some sort of cutting mechanism. Let's see cutting mechanisms. Now cutting mechanism may have some sort of rotating blade or some sort of cutter. So a cutting mechanism will be actuated using something like a convert EE to rotational. Okay, and you will supply. Okay, so this is the supply to the cutting mechanism. So so the supply is coming to first to the conversion unit, where electrical energy is converted into rotational energy, and then it cuts. So when it cutting energy cuts, it will also stop. Okay, so the processor again give a signal when to stop or cut. Okay, and then you dispense the sachets. So as an output, you have the sachets, the cut sachets. So basically, this is how you are connecting now a sachet to sachet. Similarly, when you are cutting or dispensing, probably there are energy lost in terms of heat or in terms of heat loss or noise. So those are actually your sound output and heat out. Okay. And once these are done, then MCU will probably give a signal that confirmation is done. So what we missed here? So what we missed here is like human energy. See, for stacking this essay, probably human energy is required. Okay, so this is double line. Okay, because this is material. Again, for to feed you do not need. Okay, and for storage, probably you need to have some sort of utility box, so that those can be secondary functions. So you need some utility, storage chamber. So those are like requirements, not functions. Okay, so stores as a itself is a function, so no need to write here how to do that. Okay, so this is an example how we can actually use flow model for a new product like a sachet dispenser. And you can see we have critical functional blocks, but we have lot of dependencies, interdependencies across the various critical functional blocks. So because of that, it is not easy to represent this in form of a simple tree structure. Okay, not possible. So we end up having something called function structure. Okay, not function tree. So where basically we have multiple in individual critical function parts. So this is one critical function path, this is one. So likewise we have four critical function here. So for example, the very high level function can be sachet dispensing, but then first level sub function we may require to store sachet, dispense sachet, detect sachet, and cut sachets. Okay, then for storing we need to arrange it, then get the correct number. For dispensing we need to feed the sachets, then activate the roller. Okay, for detecting sachet, before that activate sensor, then detect rolling, then cut sachets means activate cutting mechanism, then get sensor information. So see, there are interdependencies between different critical paths. Like activate sensor, then sensor give signal to this particular critical path. Similarly, activate roller, so it will detect roller. Okay, so likewise, in a function structure, we try to represent various critical paths along with their dependencies, and this is how we map various level functions in a function structure. Clear? If you have any doubt, please feel free to ask. Okay, you can use the message box. Okay, so next thing is like how to transform these product functions into a particular form, because at the end we need to have a concept, if a product which have some sort of physical existence, that's where we want to reach. Okay, so what we call is something called as product architecture. So product architecture is basically the scheme by which the functional elements, so just remember these terms, it's a particular scheme. What do you mean by scheme? Scheme means different possibilities. Okay, different possibilities. Okay, or different particular settings, setups by which the functional elements of the product are arranged into physical building blocks. That means in a particular functional tree or functional structure, you may have various relationship, various tree structure, but how you arrange or group them in a particular physical building blocks, that's what define the architecture of the product. So for example, here if you see, the here is the engineering design of that particular negative that particular sachet dispenser. We have mainly four functional blocks. So we have many functional blocks. Basically we have four physical entities. Okay, so basically the architecture comprised of four main functional blocks, functional elements. One is the sachet holding unit, which basically define this entire critical path. Okay, probably here we try to define the storage part. Okay, so from here it is a bit difficult, but from here it is easy. So using the function structure, it is very easy to arrange into physical blocks. So it has a sachet holding unit, a dispensing unit, a detection system, and a cutting mechanism. So apart from that, it has a power unit and a microcontroller unit. So basically the detection unit have the sensor, okay, and these various elements and parts which make sure that sachet travel in these particular directions, and where how this particular sachet can be cut, that also you know are taken care by this particular detection system. And then we have cutting mechanism, which converts the E energy to something rotational using a stepper motor. Then we have something, a mechanism where rotational motion is again converted into rotational to linear motion to cut. Okay, this sachets. Then sachet holding units, where we have the sachets. They are arranged in a particular way where multiple sachets can be stacked, and the end of this particular sachet actually get fed in this particular dispensing mechanism, where there is a roller, and this particular end actually is fed here. When this roller rotates, again electrical energy is converted into rotational energy. So they generate a torque between these particular rollers. So there is a gear assembly to generate that particular torque, and then the sachet starts rolling forward. The detection system detect the sachets, and the cutting mechanism cut, and finally sachets come out from this particular slit. Okay, so this is how you define the architecture of a product based on their functional model. Okay, clear? So a product, okay, may have multiple functions, but a architecture define how the individual functions are categorized to come up with a particular architecture. So there are two kind of architecture. One is portfolio architecture, and another one is product architecture. Portfolio architecture means when an organization have range of products having a similar functional model. Okay, so there can be a single functional model. Okay, and but by grouping them in a different order, like this, by grouping the individual functional elements in a different way, you build a range of products having different architectures. So we call these a portfolio architecture. The another thing is product architecture. Product architecture is basically individual product architecture, which is again this one. So individual product is same, like you have modules, within the modules you have some sort of functions. This is what product architecture. So there can be multiple product architectures, sometimes like three functional blocks, like physical blocks, then sometimes four physical blocks, sometimes different set of functions within three physical building blocks. So we can have portfolio of architecture. Okay, clear? So if you have any doubt, please feel free to ask. I think that's the end of today's class. Okay. Okay, so in today's class, I try to cover some of the topics which are useful for functional modeling, especially for developing complex products like byte or a new product development like this as a sponsor. So these are useful techniques using which you can actually come up with product architecture, and then we can later move for product conceptual design. Okay. I hope this session is useful. So in the next session, I will cover some of the topics from product architecture design, and please be there in the class. So next class will be next Tuesday, same time, 6 p.m. So if you have any doubts, uh, please feel free to ask. Okay. Okay. Thank you. Bye.